All right, let's talk about one of the most feared, but also one of the most powerful concepts in programming, pointers. We're going to demystify them today. And you'll see they're actually a really elegant answer to a huge, fundamental question about how our computers even work.
I mean, seriously, think about it for a second. Right now on your machine, you've got tons of stuff running. Apps, files, the browser, it's all just data. So how in the world does your computer keep track of millions, maybe billions of pieces of data all at once without just losing its mind? Well, the answer is pretty cool. It's all about a system of organization that's a lot like building and navigating a massive, sprawling digital city.
So, every city needs to be built on something, right? You need land. And in the world of computing, our landscape is what we call memory. Just picture it as this vast, perfectly organized grid of empty plots, just waiting for us to start building.
And let's talk about just how big this landscape is. Take a look at this number. That is how many individual plots of land, we call them bytes, you'd have in a computer with just 256 megabytes of RAM. That's kind of old school by today's standards. And it's still over 268 million unique spots to store information. The scale is just enormous.
Okay, so with millions of these little plots, how does the computer find any single one? Simple. Every single byte has its own unique address. It's a number that pinpoints its exact location. Now, you'll often see these written in what's called hexadecimal. Looks a little weird with letters and numbers. Don't worry about that for now. Just think of it exactly like a street address for a house. No two houses can have the same address. It's the only way to find anything.
All right, our landscape is mapped out. Every plot has an address. It is time to start building. And the houses we're going to build to actually store our data, well, in programming, we call those variables.
And just like a real house, every variable has three really important things you need to know about it. First, it has a name, something we can call it, like n here. Second, it has a type. Is it a bungalow? A skyscraper? This tells us what kind of data it's built to hold, like an int for holding whole numbers. And third, and this is the big one for us today, it has a memory address. It has a location on our digital map.
So when you, the programmer, write a simple line of code like int n equals 44, you're basically handing the computer a set of blueprints. You're telling it, hey, go out into that memory landscape, find me an empty spot, and build a house that's big enough for an integer, that's 4 bytes by the way, name that house n, and while you're at it, put the number 44 inside. And the address of that whole house? It's just the address of the very first byte where it starts.
Okay, so we've got these houses, these variables, all over our city. But what if we don't care what's inside the house for a minute? What if what we really need is its street address? How do we ask the computer for that? Well, there's a special tool for exactly this job.
That tool is the ampersand symbol. We call it the address operator. Whenever you stick this little guy in front of a variable's name, you completely change the question you're asking. You're no longer saying, hey, what's inside? You're saying, hey, where is this thing located?
And you can see the difference right here. It's crystal clear. If you ask the computer for n, what do you get? You get its contents, 44. But if you ask for and n, the address of n, what do you get? You get that hexadecimal memory address. See? Totally different questions, totally different answers. This is a super important distinction.
All right, now this is where it all comes together. This is the big idea. What if we wanted to create a new variable, but we don't want it to hold data like the number 44? We want its only job to be remembering the address of another variable. We wouldn't build another house for that, would we? No, we'd plant a signpost, and that is what a pointer is.
Let's look at the code for making a signpost. Int pn is equal to n. Okay, what's happening here? We are creating a brand new variable, our pointer, and we're calling it pn. Now, because it's its own thing, a signpost is a physical object, right? It gets its own memory address. It has to live somewhere. But what's the value we're storing inside pn? It's not a number like 44. It's the address of our house n. It is literally storing the location of something else. It points to it.
And this is the absolute key takeaway. If you remember one thing, make it this. The value of a pointer is an address. That's it. A regular variable, our house, holds data. A pointer, our signpost, holds a location. It's a locator. It's a map marker in our digital city that says the thing you're looking for, it's over there.
Okay, great. So we've got these signposts planted all over the city, and they're pointing at different houses. That's useful, but how do we actually use the signpost? How do we follow where it's pointing to see what's inside the house?
we need another tool for this, and that tool is the dereference operator, which, yep, it's that asterisk again. When you put an asterisk in front of a pointer's name, you're giving the computer a command. You're saying, hey, I don't want the address you're holding. I want you to follow that address. Go to that location and tell me what you find inside the house.
And this is what's so cool about it. The address of operator, the ampersand, and the dereference operator, the asterisk, they are perfect opposites. They're like plus and minus. Watch this. You start with the house, n. Its value is 44. Then you use the ampersand to get its address. Now you have and n. Then you immediately use the asterisk to follow that address. What do you get? You're right back at the house with the value 44. They completely cancel each other out. It's a perfect round trip.
So you might be thinking, okay, I get it, addresses, signposts, but why? Why is this so important? Well, because this entire system of addresses and signposts gives us an unbelievably powerful and efficient way to manage our whole digital city. This is where we get into the really cool stuff, the advanced city planning.
One of the most mind-blowing things you can do is something called pointer arithmetic. Yeah, you heard me right. You can do math on addresses. This lets us just walk down the streets of our memory city in a really predictable way. It's absolutely perfect for when you have a whole row of houses, like with an array.
Now look at this. This is so clever. If we have a pointer, p, pointing to an integer, and we tell the computer to add 1 to it, you'd expect the address to just go up by 1, right? But nope, look, it increases by 4. So what's going on? It's because the computer is smart. It knows that our integer house takes up 4 bytes of space. So when we say add 1, we don't mean add 1 byte. We mean move to the next house on the street. It's like context-aware GPS for your memory.
And all of this leads to one of the biggest reasons we use pointers, pure raw efficiency. Think about it. Let's say you have a function, like a contractor you want to hire to renovate your house. Would you build an entire perfect replica of your house for them to work on? Of course not. That's a huge waste of time and resources. You just give them the address. That's what pointers let us do. We pass the address of our data to a function, not a copy of the data itself. And that means the function can work on the original house, making changes directly. It's so much faster and more powerful.
So there you have it. We've built this entire digital city. We have our houses, our variables, and every single one has a unique address. And we have our signposts, our pointers, to help us find our way around. The bottom line is that pointers give us this incredible, direct, low-level control over memory, and that's what makes them so powerful. So I'll leave you with one last little brain teaser to chew on. If a pointer is a signpost that points to a house, what in the world would a pointer to a pointer be? Think about it. It's a signpost that points to another signpost. Thanks so much for joining me.